Let us see 3 examples today. In the first example, consider the polynomial ring. In these indeterminates or unknowns x1, x2 up to xn, where K is a field. That means the elements in this ring are multivariate polynomials in these unknowns, and the coefficients are coming from this field K. We have already considered and studied this ring to some extent in Herstein's topics in algebra in the last section on ring theory. Now let us choose an irreducible element in this ring. Let f in A be an irreducible polynomial. Because f is irreducible, by definition f is not a unit, then f is not a unit. Not a unit, of course, means that f does not have a multiplicative inverse in the ring. And so, the principal ideal that f will generate is not equal to the entire ring. In other words, this principal ideal is a proper ideal of our ring. Our ring, of course, this one is A, the entire ring A. Okay. Now we want to show that this is not just a proper ideal, but actually it's a prime ideal. Okay, and for that, you see, we already have this fact that it's a proper ideal. So to now show that it's a prime ideal, what do we need to show? We will take any two elements of the ring such that their product belongs to this ideal. If we can then show that at least one of the elements belongs to this ideal, then by definition it will be a prime ideal. So let's take two elements. Let G and H be two elements in A. Such that their product belongs to this. What does it mean? It means that GH is a multiple of F by some ring element, or in other words, maybe I can write then here. As a result of this, then F divides GH. Now since F is irreducible and F divides GH by a result from Herstein, F will either divide G or H, and that exact result is the corollary. There is only one corollary to lemma 3.11.2 from Herstein's topics in algebra. Either F divides G or F divides H. However, there is a catch. The catch is that the way this corollary has been, and in fact the lemma itself has been stated, it only works means in the book it has been stated for unique factorization domains, not any ring. Is our ring a unique factorization domain? Yes, it is. Luckily it is. And that is why we can apply this result here to draw this conclusion. Note that by, and that also follows from another result of Herstein, and that result is corollary 2 to theorem 3.11.1. Again, we need to write Herstein. A is a unique factorization domain, UFD. Okay, so that's why we are able to have this. So, if this is true, then G belongs to this principal ideal, or if this is true, then H belongs to the principal ideal. So, the principal ideal is prime. So, that's how in this very important ring, any principal ideal generated by an irreducible element will be a prime ideal. So, that way you have many prime ideals, or hence this is a prime ideal. This multivariate polynomial ring, this of course is not a single ring but rather a class of rings, is important in algebraic geometry very much. Okay, so this was our first example. Next we go to a more familiar ring, our ring of integers. We already know that every ideal in the ring of integers is a principal ideal. That actually is a consequence of the fact that the ring of integers is a Euclidean ring. The exact result I am referring to this. Consider the ring of integers Z, and the result is this by theorem 371 Herstein, every ideal in Z is of the form this. It is generated by a single integer where m is an integer. It's a principal ideal. We can in fact assume without loss of generality that m is non-negative. I am not going to say why or how. This is something very easy. Okay, I want you to be able to figure it out yourself. Why we can choose m to be non-negative. Alright. Now, for what type of m's shall we have a prime ideal in this ring? Let us first consider the value m equal to 0. If m is equal to 0, then of course the ideal generated by m is the 0 ideal, and that is a prime ideal. The verification that the 0 ideal in the ring of integers is a prime ideal is so straightforward that I am leaving this to you. Remember, you have to show two things. You have to show that this is a proper ideal, which is almost evident, and the other thing is that if the product of any two integers is in this ideal, then at least one of them has to belong to the ideal. That's what you have to prove. Okay, so you please do that. Alright, so the 0 ideal is a prime ideal. Besides that, what other values of m can give us prime ideals? If m is prime, that means if m is a prime number, then also it's a prime ideal. I mean, this one is a prime ideal, and this is a result from, again, Herstein. And the result is lemma 377 by lemma 377 Herstein. Actually, that lemma says that this is maximal, but we already know that every maximal ideal is prime, and hence prime. Okay, so if m is 0 or a prime number, then we are getting prime ideals. Conversely, let the ideal m be prime. Okay, now the ideal is prime, that is our hypothesis. If m is equal to 0, then fine. Okay, because we have already indicated that 0 is a prime ideal. So let m be greater than 0. Now note that since our hypothesis says that this is a prime ideal, so obviously it's a proper ideal, and that's why, since m is a proper ideal, in this case this is the entire ring, the ring of integers. So m cannot be equal to 1. Okay, m is greater than 0, but because of this m also cannot be 1, because the integer 1 generates the entire ring. So m has to be greater than 1. We actually want to show, we are claiming that m then needs to be a prime number. Say that is not true. Suppose m is composite, then m is a product like this for some integers a and b, both of which are greater than 1. Okay, now what is AB? AB is m, and obviously this belongs to the ideal generated by it. And what is our hypothesis? That this is the prime ideal. So either A has to be in this ideal or B has to be in this ideal. Since m is prime, A belongs to m or B belongs to m. But then what do we get? That is, m divides A or m divides B. Is that possible? No, that is not possible, because A and B are both positive integers, both greater than 1, and AB is equal to m. So A and B needs to both need to be strictly less than m. So being strictly less than m and at the same time positive integers, none of them is divisible by m. If you are still a little doubtful about this argument, I want you to really go through the details and number theoretically show that this is not possible. Okay, so that I am leaving to you, it's an elementary thing. But this is impossible. This means that something has gone wrong, and this is the only place where something went wrong, our supposition. So, our supposition is wrong, i.e. M needs to be prime. So we see that in the ring of integers, the prime ideals correspond to the prime numbers and the integer 0. Now whatever we did with the ring of integers can also be done with a polynomial ring in one variable, one indeterminate. And similarly, we have the result that in that polynomial ring also, the prime ideals correspond to the 0 ideal and the principal ideals generated by the prime elements in the polynomial ring, which are just irreducible polynomials. In short, I will just say this. The above arguments can be adapted for the ring Kx1, where K is a field. But the question is, what is the justification for that? If I simply say that whatever we did here with the ring of integers can also be done with this ring, what's the justification? What am I using to back this up? The thing is that whatever we did here, no, that actually hasn't used anything special about integers. We simply used the fact that the ring of integers is a Euclidean ring, and that same fact is available with this ring as well. This is also a Euclidean ring. Note that both the ring of integers and this are Euclidean rings. So in both of them, all ideals are principal ideals. All the things that you have in Euclidean rings are true in both of them. Okay, so we have similarly here also. However, if the number of indeterminates increases, then things change. If you have, say, another indeterminate x2 or more than that, then it's no longer true. I mean, in such multivariate polynomial rings, it is no longer true that the prime ideals or maximal ideals can be linked to irreducible polynomials, or some such links are not available here in the multivariate case. Let us see why. Now, let n be greater than 1 and consider the ring A, which is our polynomial ring. Where K is a field. Why is this ring so important in algebraic geometry? That's the very interesting question to answer. I also don't know fully. Just like you, I have also only started studying this. Okay. So where you are, there I am also standing. So we will see. apparently this ring is very deeply linked to geometry of curves, surfaces, those things. And apparently, see how interesting it will ultimately be, it's going to be that ideals play a role in all of these things. That common, I mean something should be common, no? We are saying that we are studying ring theory. On one hand, we have the ring of integers, which has arithmetic objects, integers. On the other hand, we are saying that we have geometry, where we have geometric objects, points, lines, surfaces. It turns out that in some sense, prime ideals, in one hand, in the arithmetic world, it corresponds to prime numbers. In the geometric world, it corresponds to points. Where K is a field. Alright. Let us now consider a homomorphism, a ring homomorphism. Define the map psi from A into K, and the definition of psi is this. So what psi does is that psi maps this ring A into the underlying field K. What is the rule? You take any multivariate polynomial f from the domain of psi, and the psi image of f is that field element that you will obtain if you evaluate that polynomial at 0. Okay, so if you do that, then you will get a field element, and that field element is, I should perhaps be a little more clear about this f of 0. When you say f of 0, say you have a single variable polynomial, say x cube plus 3x minus 2, this quadratic polynomial. If I say f of 0, you know what it means. You have to substitute 0 for x and you will get minus 2. If instead I have a polynomial like this, say x1 cube minus 5, x1, x2 plus 3. What does it mean to have 0 here? It means that both x1 and x2 are 0. Okay, that thing. Then also you will ultimately get a scalar, which will in this case be an element of the field. So what psi does is that it gives us the evaluation of f at 0. It's a well-defined mapping, and you can prove in an extremely straightforward manner that this is actually a ring homomorphism in our sense. Verify that, so this is a task for you. Psi is a ring homomorphism, okay, whose kernel consists of all the polynomials in A with 0 constant term. The multivariate polynomial that I wrote here just now, you saw that in that there was that minus 3. Okay, so every multivariate polynomial, just like single variable polynomial, will have a constant term. If that is not present, then this is 0. You can almost instantly see that This is precisely the kernel of psi, because if a polynomial does not have a constant term, then evaluating it at 0 will give you 0, namely that constant term, and the converse is also true. Okay, so this is the kernel of this homomorphism. Moreover, psi is onto, which is very easy to see. Why is psi onto? You take a field element, that field element itself is a polynomial, constant polynomial, whose psi image by definition is that field element, and that is why it is onto. Hence, by the first isomorphism theorem for rings, if you form the quotient of the ring A by this kernel, it then becomes isomorphic to the field K. Isomorphic to the field K means this is also a field, and because this is a field, this ideal has to be a maximal ideal. Thus, this is a maximal ideal and hence a prime ideal also. Maximal implies prime. So, in this multivariate polynomial ring, you have got this particular prime ideal, but it is not a principal ideal. Unlike those cases, it is not even a principal ideal. Forget about being generated by an irreducible element, that is not the case here. And see, there you just need to write one line to justify why it is not a principal ideal. Since x1, x2, all these things are themselves polynomials. They are monomials, but they are also polynomials. Each one has constant term 0. So, they belong to the kernel of psi. So, that is why this is not a principal ideal. But this last line won't really be clear to you. So, let me show you something in the case where n is equal to 2. Okay, let us see here, and the general case you can then write from that. Let us consider this. Say this is our ring now, x1, x2. If you investigate a little about this kernel, you will see very easily that in this case, the kernel takes this form. Fx1 plus gx2, where f and g are coming from A. Fx1 means f times x1, okay, product, plus gx2. Okay, it's not a very difficult thing to see that the kernel will look like this. So, from this you can guess the general case also if there are n variables involved. Say we want to show that this ideal is not a principal ideal. This is something which you may have already seen in number theory somewhere, not in Herstein's book. Suppose forcefully that it is a principal ideal, then kernel of psi is generated by some one polynomial h for some h in A. Alright. Now note that we are free to choose these polynomials f and g from A. So I can choose f equal to the constant polynomial 1 and g the constant polynomial 0. That way I get x1. Since x1 belongs to the kernel, so what will happen? x1 belongs to this, so x1 is equal to L times h for some L belonging to A. Alright, so you have got the polynomial x1 as a product of the two polynomials L and h. Since, now let us think of this ring A. The ring A can also be thought of as this: kx1 x2. What is this? This is also a polynomial ring, a single variable polynomial ring, where the variable or unknown is x2 and the coefficients are coming from this polynomial ring kx1. Actually, this is how you can realize this multivariable polynomial ring. In some definitions of this type of rings, this is how they are defined recursively, by adding more and more variables. How is this justified? I mean, if I just simply think of it, say you consider a polynomial in these two variables x1 and x2. Anything, say 5x1 cube plus 4x1 square x2 plus 3x1 x2 cube. How can you view this, which is an element of this ring, also an element of this ring? Well, that's not very difficult to see. You collect the highest, the power of x2, which is the highest, you collect that, you take that and put it first, plus, then the next highest, and then the term which does not have x2. So do you not see that this is a polynomial in x2 whose coefficients themselves are polynomials in x1? Yes. So that is how it turns out that actually these two rings are isomorphic, so they can be regarded as the same thing. So we can now treat all our things that we have in this equation as polynomials in x2 whose coefficients are polynomials in x1. Okay, this we can do. And if with that idea or with that thing in mind, we apply the degree formula to both sides, what shall we get? As a polynomial in x2, x1 is constant, so its degree will be 0. By the degree formula, the right hand side will be degree of L plus degree of H. Is the degree formula applicable? Can you use it? Yes, you can use it. The place from where your coefficients are coming need not be a field. It just needs to be an integral domain, which it is. Okay. All these polynomial rings are integral domains. So this one also is an integral domain. So there the degree formula works. Thus, degree of L is also 0, degree of H is 0. We are not really interested in this one. So degree of H is equal to 0. What is the interpretation of this equation? It tells us that as an element in this ring, as a polynomial in x2, H is a constant polynomial, or in other words, if you write out H, its expression, x2 will not be there. So it will entirely actually be a polynomial in this kx1. This implies H belongs to kx1. But there is another thing also, there is another way of viewing this whole thing. Also, since you can interchange x1 and x2. I hope you can see how. If you want a rigorous proof, I have one proof, but these are things that you can just assume to be true. Okay, there is no need to really rack your brain on these things. There are more important things. We similarly have, so whatever we did by considering the polynomials as polynomials in x2, we can also do with them as polynomials in x1. So that way H will simultaneously belong to kx2. That means in one hand we are saying that in the expression for H there is no x2, and this one tells that there is no x1. So actually there is neither x1 nor x2. So H then has to be a filled element. It really is now a constant. H belongs to K. Now, what is this kernel? Can this kernel be the zero ideal? No. Why? Because the zero ideal, of course, has only the zero polynomial. However, our kernel has x1, x2, these things are there. So it's not the zero ideal. Since this is not equal to the zero ideal, so H is not equal to 0. However, at the same time, H is in fact an element in the kernel. So the psi image of H should be equal to 0 because it belongs to the kernel. Which however is H of 0. Now combined with this information that H actually is a field element. So if you evaluate H is a field element means it's constant. If you evaluate that at 0, what will you get? You will get just H. And you have got a contradiction that H should not be 0 and also should be 0. That is why this supposition is wrong. Is not, it cannot be a principal ideal. I want you to adapt this argument for in the general case where you have any n in place of just 2. It is straightforward. Okay, don't think that there are some unusual twist, or if you increase n then things really change. No, nothing essentially changes except n. N itself changes. So what is the what is our conclusion then from all of this? See, the conclusion is that in the general multivariate polynomial ring where there are more variables than one, this kernel of psi is a prime ideal, but it is not even a principal ideal. So it cannot be linked with any irreducible element or anything the way we linked prime ideals with irreducible elements in the ring of integers and in the polynomial ring where there is only one variable. That's the point. And let us see another thing. 3. This is the third example. We are now going to define a principal ideal domain. A principal ideal domain is an integral domain in which every ideal is principal. For example, a Euclidean ring. Any Euclidean ring is a principal ideal domain. Alright. Now we have already seen that although every maximal ideal is prime, but the converse is not necessarily true. For example, in the ring of integers, the 0 ideal is maximal, it's prime, but it's not maximal. The principal ideal generated by the integer 2, for example, is a proper ideal of the ring of integers which properly contains this ideal. So this is not maximal, but this is prime. However, if the ring is a principal ideal ring and the ideal you are considering is not 0, then if it is prime, then it will also be maximal. In this case, the converse is true. Let us see how. Let A be a PID, principal ideal domain. Let us consider a non-zero element in B in A such that the principal ideal generated by that element is prime. Keep in mind that every ideal will look like this. Every ideal by definition is a principal ideal. That is why when we are considering prime ideals, they will also look like this, and we want it to be non-zero. So we have chosen X non-zero. Now you see, there is one thing that is immediate. Can this ideal be equal to the entire ring? Obviously not, because it's a prime ideal, so by definition it's a proper ideal. Alright. Now to show that it is maximal, what will you do? You will consider another ideal which properly contains this ideal, and then you will have to show that that other ideal is equal to the whole ring. That other ideal also, just like this one, has to be a principal ideal because we are in a PID. That is why we are taking that other ideal, and first we are taking the element that will generate it. So let y belong to A such that this. Recall that in this book this symbol denotes proper inclusion, proper subset. Okay, so now what will happen? Obviously x is an element of this ideal, so x will belong to this y as well. And so y is y times something, say y times z is equal to x for some element z in the ring A. Now we are going to use the fact that this is a prime ideal. This belongs to x, which is prime. So either y will belong to x or z will belong to x. But actually we cannot have this. Let's see why. If y belongs to x, then every multiple of y by ring elements will also belong to x because x is an ideal. However, the set of all multiples of y is this ideal. So this ideal will then be a subset of this ideal. Is that possible? No, because it already contains this ideal properly. If the reverse containment is also true, they have to be equal. This, however, says that they are not equal. Then this is a subset of x, which is not possible. So this option is ruled out. That means we must have this. Thus, z must belong to x. So z will be equal to xt for some ring element t. Alright, now we can use this equation here. So what shall we write? In place of z we will write xt. So that way we will get yxt is equal to x. Now note that we are in a Euclidean, we are in an integral domain because a PID is an integral domain by definition, and x is non-zero. So we can cancel x from both sides. This gives, after cancellation you get this yt is equal to 1. The problem that we often face in Harstein's topics in algebra, where an integral domain by definition does not necessarily have a unit element, that means identity element 1, is not present here, because in this book an integral domain by definition has a 1. Okay, so there is no problem cancelling x. So we now have this. Thus 1 then belongs to the ideal generated by y. Why? Because yt is 1 and this is an ideal, so the multiple of y will belong to the ideal. So that way 1 belongs to I and y, and so this is equal to 1, that is A. this shows that between this ideal and A, you cannot squeeze in a proper ideal properly. Hence, this is maximal. Actually, this works in the ring of integers also, because it's also a PID. Being a Euclidean ring, it's a PID. So that is why you see, or you saw that example where we have a prime ideal which is not maximal, that is the zero ideal. Any non-zero prime ideal in the ring of integers is maximal. Okay, so as far as non-zero ideals are concerned, in the ring of integers, prime and maximal mean the same thing. So that will be all for today, whatever it is. And I won't say what we have tomorrow or try to guess. We will see what we have tomorrow. So that's it. Until then, this is me. See you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.